Let me ask you something. Have you ever dropped, say, your keys and your phone at the same time? Did you ever stop to notice which one hits the ground first? Well, today, we're going to dive deep into the physics of free fall, and I think you'll be surprised to find out that what goes up and what comes down is all governed by one beautifully simple rule.
All right, let's start with a classic thought experiment. You're standing there with a heavy hammer in one hand and a light, fluffy feather in the other. If you drop them both at the exact same moment, which one's going to hit the floor first? Come on, go with your gut feeling.
If you're like pretty much everyone on the planet, your brain is probably screaming, the hammer, duh, right? I mean, we've all seen a feather just kind of waft its way down. It feels like basic common sense that heavier stuff falls faster. But what if I told you that your common sense is about to get a major physics upgrade?
Yeah, that obvious answer is actually one of the biggest misconceptions in physics. It's not that your eyes are playing tricks on you, it's just that they're not seeing the whole picture. There's an invisible culprit at play, something that's always there messing with the results, the air itself.
Here's the deal. In our world, air resistance acts like a tiny invisible parachute on everything that falls. For something dense and heavy like a hammer, that little parachute doesn't do much. But for something light and spread out like a feather, whoa, it's a total game changer. And that is exactly why our everyday experience can be so misleading.
So to find out what's really going on with gravity, we have to strip away that pesky air. We need to imagine a perfect scenario, a vacuum, and see what the pure laws of physics have to say.
Okay, prepare to have your mind bent a little. What if I told you that an object's weight, its mass, has absolutely zero effect on how fast it accelerates downward? What if gravity treats a feather and a hammer exactly the same?
You know, for almost 2,000 years, even the greatest thinkers on Earth, like Aristotle, were totally convinced that heavier objects fall faster. It was just accepted science. But then this guy, Galileo Galilei, came along, and he dared to ask the question, yeah, but is that really true?
So, let's fast forward a few centuries. The year is 1971. The location isn't a tower in Pisa, it's the moon. An Apollo 15 astronaut, David Scott, is standing on the lunar surface. In one hand, he has a hammer, in the other, a feather. He's about to put Galileo's big idea to the ultimate test, in a perfect vacuum with the whole world watching.
He lets them both go. And what happens next? Oh, it is just one of the most stunningly beautiful moments in all of science. The hammer and the feather, they fall side by side, in perfect sync, and they touch the lunar dust at the exact same instant. Galileo was right.
So what is this incredible universal rule that's pulling them down together? Well, it all comes down to a single magic number. You can think of it as the engine of free fall. But first, let's get our terms straight. When a physicist talks about free fall, they mean this pure, idealized state. It's an object moving only because of gravity. No air, no friction, nothing else getting in the way.
And here it is, the secret ingredient. On Earth, we call this number g, and its value is 9.8 meters per second squared. Now, what on earth does meters per second squared mean? It's simple, really. It just means that for every single second something is falling, its speed increases by 9.8 meters per second. It's like gravity is flooring the accelerator.
Just think about it like this. After 1 second of free fall, an object's moving at 9.8 meters per second. After 2 seconds, it's going 19.6. After 3 seconds, 29.4. See the pattern? It's this relentless, perfectly predictable increase in speed. And it doesn't care one bit if you're a hammer or a feather. So here's the really cool part. Because this acceleration is so constant and predictable, we can actually calculate the motion of any object in free fall with crazy accuracy. All we need is the right toolkit.
Okay, don't let the equations scare you off. You don't have to memorize them. I want you to think of them as a set of 3 superpowers. With these tools, you can predict the future. Well, the future of a falling object, anyway. You can figure out exactly where it's going to be, how fast it'll be going, and precisely when it'll get there.
All right, enough with the theory. Let's put these superpowers to the test. We're going to use them to solve a classic physics problem, tracking the journey of a baseball.
So here's the scenario. A baseball gets hit straight up into the air. Exactly 5 seconds later, it's caught at the same height it started from. The mission, if you choose to accept it, is to figure out the maximum height that baseball reached on its journey. You ready?
Now, we're not just going to guess here. We're going to approach this like a physicist. First, we set our directions. We'll say up is positive and down is negative. Then, we list out all the clues. our knowns and unknowns. And finally, we choose our weapon. Our equation.
Okay, let's lay out the clues we have. We know the total time the ball was in the air, 5 seconds. We know the acceleration from gravity, which is negative 9.8 meters per second squared, since it's pulling down. Our goal is to find the max height. But there's a hidden clue here, a secret that's going to crack this whole thing wide open.
And here it is. This is the golden ticket to solving the problem. At the very peak of its flight, that tippy-top point, for just an instant, the baseball stops moving. It's not going up anymore, and it hasn't started coming down yet. Its velocity is 0. That little fact is everything.
So we take that key insight, we plug our numbers into the right superpower equation, we do a little bit of math, and we get our answer. The maximum height the baseball reached was 30.6 meters. That's over 100 feet up in the air. That is a serious pop fly.
But wait, there's more. The math also reveals some other cool stuff. The trip was perfectly symmetrical. 2.5 seconds to go up, 2.5 seconds to come down. It left the bat going up at 24.5 meters per second, and it landed in the glove coming down at the exact same speed. And here's the wildest part. Even at the very top, when the ball was literally motionless for a split second, gravity was still pulling on it with that same constant force. Gravity never takes a day off.
So we've kind of cracked the code for free fall in a perfect air-free world. But that brings us right back to reality, doesn't it? If gravity is always accelerating things, then why does a skydiver eventually hit a top speed, a terminal velocity, and just stop getting faster? What's putting the brakes on? Well, that is a fantastic question, and a story for another time.